All right, our next speaker is a very recently local speaker, now at CUNY, Ivan Morozov.
Thank you. Um, Thank you, Mel, for organizing this conference. It's a pleasure to talk. I actually have a last minute addition to this topic that has nothing to do with this about one of last year's CANT open problems that I'll mention at the end of the talk. So we can start with something simple. We'll note the by Wilson's theorem, this expression right here is going to be an integer if and only if n is prime or 1. And the integers that this theorem generates, they're called the Wilson's quotients. And there's a natural extension to this, which exists. It's in literature. If you split the n-1 factorial term along some parameter k between 0 and n-1, and then you get this term involving the n-k-1 factorial and the sum involved with the Stirling numbers of the first kind. And we'll reference the fact that this family of Stirling numbers that appear here, they can be expressed as -1 to the k times k factorial. And because n-1 factorial is congruent to this expression modulo n, there's a corollary for non-negative integers and k less than n. This is going to be modulo -1. This is going to be equivalent -1 modulo n if and only if n is non-composite. And now we'll just want to see what happens if we stick this in instead of the n-1 factorial term into Wilson's theorem. And we're going to see that this is obviously an integer if and only if n is not composite. And we're going to take the absolute value for when we take the sums of these. So in 1938, Emma Lemmer gave us some congruences for the Wilson quotients. So if p is prime and we denote b sub k as the kth Bernoulli number, then we have this pair of congruences, in particularly the second one. The Wilson quotient is equivalent to the difference between the two Bernoulli numbers mod p. And we ask if there's anything, if we can extend this to the general quotients. And there actually is a very simple modification of Lemmer's congruence. We just subtract the kth harmonic number here, modulo p in the congruence. And I'll show a brief proof with elementary methods, like all of them are going to be for the rest of the talk. And here, the Wilson quotients, we take the expression that has the Stirling numbers of the first kind for I bigger than or equal to 2. We see that these terms in the sum divided by p are 0 modulo p. And so after a simple reduction and redistribution, we see that this is congruent to the general quotients plus this expression with the Stirling numbers of the first kind again. And again, we'll reference this expression for this family of Stirling numbers for the first kind. And we get that the more general quotients in the Wilson's theorem, they're just the original quotients minus the kth harmonic number. And then by substitution, we get the congruence that we want. Now, we do something pretty simple. Since we can take the parameter k from 0 to n-1, let's see if there's anything interesting we can say about the sums from k equals 0 to n-1 of these. And they turn out to be somewhat interesting. So the sum of the quotients is going to be pretty elegant to work with, and there are some clean results. But when you do it with the absolute values, it's going to be shrouded in some complexity. So, for example, the first theorem, first property we're going to see, Zn is going to be an integer for all natural numbers, and the z plus of n is going to be a natural number if and only if n is even or non-composite. So I'll show the proof of the first one, the first statement. So if n is not composite, then we're just taking the sums of integers, and so it's going to be an integer. That's simple. And if n is composite, then we take a look at this term, and suppose that n is not equal to 4, which we'll use in a couple steps. So if we take this term, the k factorial n minus k minus 1 factorial, we can expand it, then reduce it modulo n, and this product is minus n minus 1 factorial modulo n. And then using that n is not equals 4, this is 0 modulo n. And so the sum shown here is going to be, n is going to divide the sum. And since z of n is just 1 over n times the sum, it's an integer. And then we add the additional case for z4. Moreover, there are explicit formulas that we can see. So z of n has this closed formula. Notice that it's going to be just 1 whenever n is even, and z plus of n is going to be this more complex, has a more complex expression, mostly because of the 2r over r sum that doesn't reduce nicely, and we have to use some special functions like the Euler's transcendent. And I'll just show a brief derivation of this. So suppose that s is this sum over here, then z of n is just 1 plus s over n, and then we use a little bit of trickery to show that we can express s divided by n minus 1 factorial as the alternating sum of reciprocals of binomials, and there's a paper from 2004 which tells us exactly what this is, and we just substitute back using simple substitution, and we get this formula for z of n. Now there are some congruences for z of n that act as primality tests. So if n is composite, then z of n is going to be 1 modulo n, and if it's not, then it's going to be minus 1 modulo n. Z of 2n minus 1 is 0 modulo n, if and only if it's not composite. And then for z plus, it's going to be there's some more nuance. So if n is composite or 2, then it's going to be divisible by 2n. And if n is an odd prime, then z plus of 2n is going to be n plus 1 modulo 2n. And if p is an odd prime, then z plus is going to be this the difference in Bernoulli numbers, minus 1/2 times this harmonic number, which is reminiscent of our old congruence for the general quotients, and we can use it to construct this relation. I'll show a brief proof of the second statement here. The second sentence of the third statement. So if n is an odd prime, then z plus of 2n is this sum here, and then we look at the individual terms in the sum, and when we take the sum of two terms, we get this expression. But we'll see that if you take the sum of two consecutive terms, then 2n squared will simply divide this. So this sum is going to have an odd number of terms. So we just pair, let's say, the first to the second term, third to the fourth term, and the sum of each pair is going to be divisible by 2n squared. So only the last one, n minus 1 factorial times n factorial, is going to be unpaired. So there's a slightly slick use of Wilson's theorem, where we can say that n minus 1 factorial, n factorial, is congruent to minus n factorial modulo 2n squared. And Wilson quotients are always odd, so 2n squared will divide this expression here. And by distribution, we'll see that minus n factorial is congruent to n squared plus n modulo 2n, and this shows us what we want. And I'll just show generating functions, the exponential generating functions. They are not ordinary because their radius of convergence is going to be 0. They're not going to work. So there they are. They use a lot of special functions, like the lower incomplete gamma function and the Lurch transcendent. And this one for the z plus of n, it uses a lot. It even has a generating function of a Lurch transcendent inside the generating function. Okay, and now for something different. Last year there was a problem proposed about partitioning Pythagorean triples into 3 parts, and the expression for this is given with the rounding function of n squared plus 3 over 12. And from this, we can see that if A, B, and C form a Pythagorean triple, then P of A into 3 parts plus the number of partitions of B into 3 parts is equal to the number of partitions of C into 3 parts. But there seemed to be no combinatorial proof of that. So I would like to show a construction in a bit. And here are just some examples for some Pythagorean triples where this is true. And for example, for the family of Pythagorean triples where A is plus or minus 3 modulo 12 and B is 0, 6 modulo 12, then we can see that this is their sum is going to turn out to be C squared plus 3 divided by 12, which is true because from the theorem, C has to be equivalent to plus or minus 3 modulo 12. So the construction of the combinatorial proof just follows from counting lattice points. So if n is greater than or equal to 3, the partition into 3 parts, n1, which is at least n2, which is at least n3, which is at least 1, and we're going to define the coordinates of the lattice points as the difference between the parts. So P of n are the lattice points in Z cubed that satisfy this relation. So each lattice point corresponds to a partition of n, and they lie in the triangular region, in the first octant in the of the 3D space, and we can project it. We can project these lattice points onto let's say the YZ plane, which we'll define as this, and this preserves the bijection. So the number of lattice points in this region is the same as the number of partitions of n into 3 parts. And this is just to show that this is the same. And this region is going to look like a right triangle with these vertices, with the hypotenuse as being a segment of this line. And this is just to verify that indeed counting the lattice points gives us a known formula for a number of partitions of n into 3 parts. And this is just another way to express it based on congruences of n modulo 2 and modulo 3. So the way to construct this is if n is bigger than m, there are 2 natural numbers, then the right triangle for m is going to be inside the right triangle for n. And we'll show that the number of lattice points in the region where they don't overlap is the same as the number of lattice points that we expect to appear in the right triangle for B. So if C is the if the number of partitions of C into 3 parts is counted by the number of lattice points in the bigger triangle, and the number of partitions of A is in the smaller triangle, we'll see that in the trapezoidal region that's between them, it's going to count the number of partitions of D into 3 parts. And there are 6 cases that we do this based on the congruences of C modulo 2 or 3, and I'll just show you I'll just show you a picture for C1 modulo T and C0 modulo 3. It's a very simple geometric argument. So the red triangle here. So for this Pythagorean triple, A is 36, B is 27, and C is 45. The number of lattice points in the red triangle is the number of partitions of C into 3 parts. The number of lattice points in the blue triangle is number of partitions of A into 3 parts. And we want to verify that the number of partitions where they don't overlap is the same as number of partitions of 27 into 3 parts. And instead, by counting it as the number of lattice points in this parallelogram plus this triangular region, we get that this is true. And this is just how the proof looks like. So the very elementary, by just simple cancellation, this first term over there, that's the number of terms in the parallelogram region, the number of lattice points in the parallelogram region, and the second term is the number of points in the triangular region. And by simple algebraic cancellation, it cancels out.
And you're getting these counts through Hicks theorem?
No, so for the top part, so this is always a trapezoid. It will always split into a parallelogram and a triangular region. So for this case, the number of lattice points, let's say per y coordinate, let's say this is the y coordinate, is going to be the same. So it's just simple multiplication. If C is different modulo 2 or 3, maybe we'll get one lattice point less or one lattice point more per 3, let's say, y coordinates. And so we just correct for that. But otherwise, this is just simple as doing like 3 times 15 or 3 times 16 for the parallelogram region, and that this triangular region is kind of half of another parallelogram region. So it's just a geometric argument for this. And yeah, that's how it looks like, and the remaining cases are in similar fashion. And these are the references. And thank you.
Questions for Ivan? Anything from Zoomland? All right, let's think Ivan again. And our next speaker is in 12 minutes, Jeff Ligarius.